In this video, we're going to talk about functions that are defined by equations. So, for most of the functions that we've been talking about in this course, and functions are the fundamental unit pretty much that we're talking about in this class, Calculus 1. In other words, all of the processes that we do, taking limits and taking derivatives, right, those are performed on functions. And so most of the functions that we have in this class are specified in one of the two forms, and they're equivalent, they just look different, right? That is f of x equals, and then we have some formula here involving just the variable x, or they're of the form y equals f of x. So there's some formula over here. So one of those two formats. And that is really nice because we know up front that these things are functions if they're specified in those formats here. And it's easy and convenient to have them written like that. And so most of the time that's what we've been dealing with. All right, there is another way to talk about functions, and that is through equations. Okay. And so an equation, if I look at this equation right here, x squared plus y squared equals 1, right? That's not really in the form that was mentioned on the previous slide. This is the equation of a circle, right? Which I can't really write in that other format that we talked about earlier, either of those two formats here. So there's some, fundamental objects kind of that I want to look at that just can't be specified in that manner that we talked about before, and so this is one of them. Okay, so I can take a look at some equation that involves x and y's, right? And then what we really need to know here is, okay, that's fine. I see I have an equation involving x's and y's. Does the equation define y as a function of x? In other words, could I maybe specify it in one of the more convenient formats instead of this equation format here? Okay, so how would you answer that kind of question? Well, the key thing is to remember, to be a function, right? For this thing to be a function, every value of x must correspond or give exactly one value of y. In other words, if I plug a number in for x here, any number at which this expression is defined, and solve for y, I have to get exactly one value out, because that's what a function is, right? I plug in a number and I get one specific output. Okay. All right, so that's what functions do, right? And so now if I wanted to answer that question, does the equation x squared plus y squared equals 1, does that define y as a function of x? There, I have a slight typo. Okay. All right, so in order to figure that out, I'm just going to try plugging in a value for x right here. If I plug in a value for x of 0, let's say, just kind of pick that and see what I get, because that's an easy number to plug in. I get y squared equals 1, right? And that equation has two solutions, right? Y equals plus or minus the square root of 1, which of course simplifies to y equals plus or minus 1. Okay, so notice when we plugged in a 0 for x and solve for y, we get two values here. So the answer to the original question is no, that equation does not define y as a function of x. And the reason why is because an x value of 0 leads to two y values, 1 and minus 1. Okay, so right off the bat there, the very first number we tried shows us that this equation does not define y as a function of x. Okay, so it's pretty easy to show that by plugging in the 0 and showing we get two y values for an x value of 0. But in general, that's not really a very efficient or effective way of trying to determine whether or not a function or an equation defines y as a function of x or not. A tiny bit better approach is to try to solve for y without plugging any numbers first, right? So let's go back over that previous example and show you how that would go. So same question, same equation, and I'm basically going to do the same process, but I'm not going to plug in a value for x here. I'm just going to solve for y. So the very first thing I would do is subtract x squared from both sides. Get y squared equals 1 minus x squared. And then to solve for y, right, I would square root both sides, essentially, but don't forget that there are two solutions, right? The plus solution and the minus solution. Okay? And so again, we would say, well, the answer's got to be no, right? To the original question, why this equation does not define y as a function of x, because we get two solutions for y, right? Y equals the plus square root 1 minus x squared, and y equals minus square root 1 minus x squared. And so you can see if I had an x value of 0, right, it's going to lead to square root 1 and minus square root 1. And so it's pretty clear, because we get two different pieces right here, right, that the original equation does not define y as a function of x. All right, let's take a look at another example of this. Does the equation x squared plus 2xy equals 1 define y as a function of x? So we're going to take the same approach, right? We're going to try and solve for y. We would subtract x squared from both sides, right, to get all the y terms on the left side, and over here there's no y's, right? And then all we would have to do to solve for y is to divide both sides by 2x right here. And so here we get this nice, neat solution for y, right? Whatever x is, when I plug x in here, I'm only going to get one value out, right? If I plug in an x equals 1, I get 0 on top and 2 on the bottom. 0 divided by 2 is 0. So I get a unique value for y for every input for x. And so the answer here is that, yes, we got a unique solution when we tried to solve for y. So y does, this equation does determine y as a function of x. Okay? All right. So there are some other issues with this approach, and sometimes given an equation involving x and y, it might be extremely difficult or maybe even impossible to solve for y in terms of x. So the general situation can get pretty complicated pretty quickly. Here is a function involved, or an equation involving x's and y's, right? And this one, right, is not going to be so easy to solve as the last two equations that we did. Okay, so you can run into trouble with that approach pretty quickly. So the thing is, right, what we'll see later on is that even if it is difficult or impossible to solve for y, like in this one right here, we will see that it's not that difficult to find a formula for the derivative. Okay, there's a couple of things that we need to talk about first before we get into that. Number one is, well, this may or may not even be a function. How would we know that there is even a function here to take the derivative of? And so we'll answer that question somewhat in a subsequent video. Okay. So the summary here, we're not really going to be solving any equations that much for y, and like I said, sometimes it's impossible to do that. So the main thing that we're headed to is just taking the derivative of functions when they're defined by equations. So the summary here is that the best way to specify a function is in the f of x equals or the y equals f of x format. That's by far the best way to describe a function. Nice and convenient. There's no question about whether it's a function or not. We know it's a function because it's specified in that manner. So that's great when they are specified that way. Functions, though, can also be specified by equations, not in the above forms. Okay, so and sometimes we'll just need to do that for various reasons. Okay, so equations, functions can be also be specified by equations that aren't f of x equals or y equals f of x. Okay, and the final thing, right, is that, okay, if I pick some random equation, right, sometimes that equation will define y as a function of x, and sometimes they do not. So you have to be a little bit careful about doing that. There's always the question, all right, does this define y as a function of x or not?